Hello, everyone. Thank you for letting me the opportunity to present you some projects of our European community of PHIL users. I've been involved in these last years for various applications and using different power amplifier technologies and power range. So the first one, NTNU and SINTEF, they have built a national smart grid laboratory in Trondheim to provide state-of-the-art infrastructure for research and development, demonstration, verification and testing of a wide range of smart grid use cases. So this platform allows manufacturers to test and verify their new products and solutions in laboratory conditions before being commercialized. This picture of the laboratory displays the external power amplifier cabinet at the left of the slide. In front of the workstation, the cabinet with real-time simulation platforms from OPAL-RT and other cabinets with hardware from the laboratory are displayed, like multi-modular converter, as we will discuss in a few minutes. A real motor at the right of the slide, which can be interfaced with the PHIL setup, is shown. So the laboratory integrates OPAL-RT real-time simulator and external Compiso power amplifier up to 200 kVA, 400 volt AC or 700 volt DC with a 5 kilohertz bandwidth. On the HIL side, a lot of simulators can be seen. It can be used to increase the computing and the input-output capability. But just to make it simple, the OP5600 is used for running real-time models with RT Lab, while the OP4520 is used for communicating with the power amplifier with optical fiber links that you can see, using SFP ports and Aurora communication protocol, which can transfer data up to 5 gigabits per second. On the power amplifier side, at the top left-hand corner of the slide, you can see the first picture displaying the transformers and filters, which are the interface with the main grid. The second picture shows bidirectional front-end converter aiming at establishing the DC bus. Then we see the 6 Compiso digital amplifier. It acts as inverter, which offer up to 6 phases to be controlled. And finally, the matrix of contractors is shown in the fourth picture, which is used to change the configuration mode of the CDA, like free-phase voltage plus neutral, or free independent current, or DC monopolar, based on the application. The application I would like to focus at is this multi-terminal HVDC grid connecting offshore wind farm. These results belong to the Best Path project, co-funded by the European Commission. So this demo package is to consider a future scenario featuring a North Sea supergrid connecting 3 countries with a large share of wind power, so higher than 50%. 3 main AC parts are connected to a DC network with MMC. The topology can be half bridge or full bridge. And the goal is to study the control strategy, ensuring safe and stable operation of such grid, despite large variations in produced wind power. This schematic represents the PHIL implementation. So only one terminal is represented in this picture, but the real application has been done with 3 terminals. So at the right side, the hardware from SINTEF laboratory is displayed with MMC and transformers in the lab. The orange part, it represents the PHIL setup. So OPAL-RT HIL simulator, modeling a wind farm, drive and control. For example, the current to be injected is computed in the model, as it can be seen in the diagram, while the external power amplifier behaves as a voltage source. But as the MMC is applying a voltage, the other side should act as a current source. So the method used here is to implement a current control loop to make the voltage source behave as a current source. SINTEF has 3 real 60 kilowatt MMC converters in the lab. So one with 7 levels, one with 13 levels, and one with 19 levels. Current and voltages are compared for the arm of these MMC converters in 40 case scenario. And it can be seen that results between the simulation and the demonstration are matching quite well validate this PHIL approach for this project. A complete different setup here for motor testing is discussed with Plastic Omnium user case, an international company based in Levallois in France, mostly focused on the automotive industry. So the goal of this setup is to test a three-phase brushless DC motor, sensorless controller with trapezoidal back EMF at 100 watts power level in steady state. So the physical controller and the three-phase two-level inverter hardware need to be interfaced to the simulated BLDC motor to test the performance of the motor control with firstly fault scenario like open circuit and short circuit, and secondly different motor configuration, which makes the setup reusable for future applications. So the goal of this PHIL test bench is to generate and absorb power like a real DC motor. This setup is composed of different devices. Firstly, a brushless DC motor control, actual controller and inverter under test that you can see left. Secondly, an OPAL-RT OP-4500 HIL simulator in which a motor is simulated in the FPGA using finite element analysis modeling for an accurate simulation of the motor back EMF and impedance. Thirdly, TEPCO 4-quadrant power amplifier are used to interface the real voltage and current set points sent by the inverter to the simulated motor model. The motor position feedback is sent back to the controller on the test using encoder and resolver. And finally, it can be seen that the real RL impedance for each branch of the motor has been added to emulate the motor in the An integrated rack has been delivered to Plastic Omnium. So it's composed by three 4-quadrant TEPCO power amplifier with a nominal power of 400 watts. So the interest of having an amplifier nominal power 4 times higher than the motor nominal power is linked to fault case scenario. Okay, current peaks appear in the system during fault case scenario, so we need to design a high power for the power amplifier. And there is a switch which allows to connect the load in delta or star based on the application. Then we have a chassis from Vector VT Systems, which is used for fault insertion purpose like short circuit phase, open circuit per phase, or short circuit phase battery. Signals, conditioning, and monitoring are done inside 2 mapping boxes, and the OP-45 then runs the FPGA motor model, while the inverter under test is driven by a 20 kHz switching frequency. So the time step of the simulation is around 500 nanoseconds, and the theoretical precision of the model was below 1%, even in fault case scenario. Another application now is the Institute of Electric Energy Systems and High Voltage Technology in Karlsruhe. First, an OPAL-RT PHIL platform with HyperSim software is used. The OP-5030 for the computation part and the OP-5607 is used to connect simulation to power amplifier. It's mostly for network configuration model for 4-wire low voltage grid, mostly for voltage and frequency stability studies when asymmetric loads are connected. 2 Spitzenbergers and Spies linear power amplifier with a nominal power of 3 times 10 kVA, a nominal voltage of 400 volts, and a bandwidth up to 30 kHz can be seen on the slide. A current measurement unit as well, using Clearstone transducers, is included in the setup to send back the current measurement from the power amplifier to the HIL simulator. And finally, a connection between the Energy Smart Home Laboratory and the PHIL setup is done using the connection point, which can be seen at the right of this slide. But what is this ESHL? Actually, the behavior of the smart home has been reproduced thanks to this Energy Smart Home Laboratory, which is a smart residential building with metering system, intelligent appliances, distributed generation, metering system, automation, and hybrid energy storage system. The scenario here addresses the voltage quality and frequency issues. So by applying some scenario in the simulation, the hybrid electrical energy storage of the smart home laboratory should provide ancillary services like virtual inertia thanks to power feed-in. So many low voltage issues in the context of PHIL can be tested, and a classification of different power quality issues is shown in the table of this slide, and most of them are studied by KIT. So let's focus on the following test case reproduced by KIT. On November the 4th, 2006, the famous loss of synchronization scenario occurred, and the European grid was divided into 3 parts with different frequencies. So the geographical areas can be seen with the map, and the frequencies for each part are displayed in the graph. And this scenario of the West frequency zone has been applied in PHIL with Energy Smart Home Laboratory and power system simulation. The goal is to see if the hybrid energy storage system installed can provide virtual inertia as an ancillary service. And the green waveform shows that power from energy storage is fed to the power system when the frequency gap is observed. Of course, as the storage system is too small compared to the power required for this scenario, it has a negligible impact on the frequency. However, it proves that the system can provide virtual inertia, and that in a real scenario, it would have helped to reduce the frequency deviation. At Newcastle University now, for this fourth user case, a large power system model runs with RT Lab, interacting with a laboratory network and an energy storage system through a flexible power conversion system, so the AC-AC converters, as you can see. And the impact of the storage system response on frequency events is observed. So the storage is coupled to a 415-volt bus bar of the laboratory network by a DC-AC power converter, which is controlled via a real-time target computer. The laboratory network itself is energized by this 30 kVA AC-AC tri-phase power amplifier, capable of supplying variable voltages and frequencies in real time. So the goal here is to demonstrate the capability to provide a real power response to transient events, such as imbalance between load and demand taking place in a real-time simulated power network. For this scenario, the IEEE 24 bus model was used by running on one CPU core at 50 microseconds time step. The simulation was carried out using OPAL-RT solver Artemis SSN to optimize SimScape power system models for real time. Frequency events are created by step changes in demand, and the laboratory energy storage system responds to this frequency deviation according to the response capability of the storage. It is called the EFR curve. It stands for Enhanced Frequency Response. And the goal of Newcastle University with this setup is to compare different enhanced frequency response services. So this scenario displayed here is a 500 megawatt imbalance created within the real-time simulation. So it results in a substantial drop in frequency. And the figures show that the power system frequency and the power response of the storage system. So the change in frequency is observed for sure. And then the power is dispatched according to the enhanced frequency response curve. So the experiment has been done with different peak energy storage outputs: 50 megawatt, 100 megawatt, 250 megawatt, and 500 megawatt. So for sure, as the size of the energy storage system output increases, the severity of the frequency event is reduced. But it can be seen that the duration of the event was slightly increased as well. It can be explained by the fact that a reduced governor response was required as a result of the action taken by the enhanced frequency response. So the system stayed within the statutory limit, plus and minus 0.5 Hertz, only with the 250 megawatt and 500 megawatt peak energy storage system output. To conclude my presentation, I would like to focus on the Institute for a high voltage technology at RWTH University in Aachen, which is involved in the European project promotion inside the Horizon 2020 program. One of the goals of this project is to study the new challenges of meshed DC systems in the offshore area for transmission system operators. Testing with full high-scale system is challenging or even impossible sometimes due to a limited access to existing infrastructure and high safety requirements. So one solution, as presented in the schematic at the bottom right hand corner of this slide, is to use a low voltage multi-terminal DC test bench and to apply the solution found at the low power level area to the high power level domain. So therefore, PHIL is a practical and efficient way to test new control concepts and validate new components or material in the lab. The concept of the MMC test bench for MTDC application is presented at the right side of the slide. So the AC grid and wind farm simulation is running with high-precision software on the OP5707 HIL simulator. The laboratory scale MMC converters are coupled with the simulation using 421 kVA linear power amplifier from Puissance Plus. The DC system has been emulated with TI sections and interconnects the different MMC test benches. Finally, the DC grid control or high-level control is done with a master OP4510, while the MMC control or low-level control is done with a slave OP4510. This slide focuses on the MMC test bench and the TI sections used to emulate the DC link. So 8 OPAL-RT lab-scaled MMC test benches are in the lab. As you can see with this picture, it is composed by an OP4510 for the low-level control and 6 OP1210 boxes. Actually, each of them represents an arm of the MMC converter. And inside this box, there are 10 submodules to have 11 levels, a nominal voltage of 400 volts, and it can be operated as a half bridge or full bridge topology. The rated power of the lab-scale MMC is 6 kilowatts. Monopolar and bipolar network configuration can be tested by RWTH with this setup. For the DC system, 32 PI line sections are installed, which emulate 800 kilometers in bipolar network configuration and 1,600 kilometers in monopolar network configuration. To conclude this user case presentation, I simply wanted to show you a picture taken by RWTH during the factory acceptance test last year at OPAL-RT headquarters in Montreal. Only 4 MMC racks and 2 PI section line cabinets can be seen because the focus of this test was really the control of the MMC converter using OPAL-RT solution based on MATLAB Simulink for rapid control prototyping. But some deep demonstration test cases are currently being investigated by RWTH, like DC fault handling in offshore grid, or black start capability of diode rectifier connected to offshore wind farms, for example. So I would like to thank all of you for your attention. I'm looking forward to your question, and I leave the floor to Mathieu for an exciting announcement to come.